So last time we just uh, talked about the surjective function, our onto function. Um, a surjective function is a function uh, for which the each element in the codomain is an image um, under the function of the domain. In other words, you can always find a element in the domain um, to map um, to any element in the codomain under a function f. We did a few examples. Some of the examples are pretty straight, but some of them are not. We have seen a couple of them. You can define any functions. You can define on numbers, but you can define functions over sets in general. So sometimes they were not so straightforward. And another thing is we usually have a lot of piecewise defined functions, and in those cases, if we want to know whether a function is surjective, then we usually need to check it case by case, just like injective functions. So this example we saw before. The function f is defined from z to z, and is defined piecewise as this. So f of n is equal to n if n is greater than or equal to 0, and is n plus 1 if n is less than 0. So this is piecewise defined function. So we want to know whether this function is surjective. I think we did it before, and we show this function is one-to-one. So let's just see whether the function is onto or surjective. So, the typical way to show a function is onto or surjective is just to pick up any element in the codomain and to show that you can find the pre-image of the element under the mapping from the domain. So let's just pick up any integer from the codomain Z. So this because the codomain is all the integers, it can be positive, it can be negative, it can be 0. So since the function is piecewise defined, we also need to separate the cases into two in order to compare. So the first case, is when this number b in the codomain is non-negative, b greater than or equal to 0. So then you can pick up a equals b, and then what is f of a? Because a is equal to b, so and b is non-negative, so a is non-negative. So we're going to use the top formula. So f of a equals a. I mean equals a, but a is equal to b, so it's just equal to b. And obviously this a is in z. Okay, so we have shown that when element in the codomain, when it's non-negative, you can always find a pre-image from the domain Z. Okay, What happens if this number you pick in the codomain is negative? Then you just let a equal to b minus 1. So because b is negative, so b minus 1 is also negative. So f of a uh, will be f of b minus 1. But b minus 1 is negative, so you're going to use the second formula. So just plug in b minus 1 for n in n plus 1, so we get b minus 1 plus 1, which is b. So again, f of a equals b. So in this case, we also found the integer, negative integer, a such that the f of a equals b. So this a is also in the domain. So if we combine both cases, that it essentially says that for any number in the codomain, you can always find the free image in the domain. So this function is surjective, but it is not injective. And the problem is at 0, okay? Oh, -1, okay? If n is 0, then f of 0 will be 0. You have to use the top formula because 0 is greater than or equal to 0. So f of 0 is just 0. But if n is -1, then you're going to use the bottom formula. So f of -1 is the -1 plus 1 is 0. So it's also 0. So f of -1 is also 0. So that means for the number 0 in the codomain, you can find the two pre-images in the domain. So if it's not injective, it's not one-to-one. Well, I guess I did say it was one-to-one. That wasn't all right. Anyway, this is on to function. Okay. So you can see, when we have piecewise defined functions, it usually makes the situation complicated, and the way to deal with it is to separate different cases based on the definition of the function. All right, so it's one example. So the next thing we want to talk about is the range of the function. So we talk about the injective function and the surjective functions. We learned the concept of range of a function before. Now we have different things. We have codomain and we have range. So what's the difference? Well, basically the range of function is all the outputs of a function. So and this actually is a general definition. Either the function is one-to-one or injective or surjective or neither, then we can always talk about the range. So the formal definition of range is, suppose you have function f from a to b, and the range of the function is all the function values when you pick up all the elements in the domain. Okay. And we use the notation IM parentheses f to mean the range of the function or image, So obviously, the image of the function of or the range of the function is a subset of the codomain. By definition. You may have some elements in the codomain without free image, but all the images of the function must be in the codomain. All right, so let's look at some examples. So we need to make a distinction between those concepts. So suppose there is a function f defined on two sets, from set 1, 2, 3, 4 to the set of a, b, c, d. So you can write the function as all the pairs. So this function includes 4 pairs: 1a, 2a, 3b, 4c. So what's the image of the function? You just look at the second coordinate, right? So that would be a, b, c. The first and the second order pair has the same. So you don't count it twice. So the image is just the set of A, B, C. Or if you want, you can write it F1, F2, F3, F4. So all the outputs from the domain onto the mapping. Okay, so according to the definition, right? So this range only has 3 elements, and the codomain has four elements, so they're not the same. The range is smaller than the codomain. The next example is a function from R to R given by f(x) equal to x squared. So what's the image of the function and what's the range? This is easy to do. You want to know what the output of the function, and you can see because you square any input, so the function value can only be positive or 0. And actually, for any non-negative number in the codomain, you can always find a pre-image or a number in the domain, so that it maps to the number under f. At least, actually you can find the 2 in most cases except 0. Oh, so if you just pick up a number in the codomain, a non-negative number a, then obviously f of square root a is just square root of a squared, which is a. So it has an image of square root a, but it has another image of a negative square root a when a is not 0. But anyway, this function has the image or range of all non-negative numbers, right? Pretty straight. The next example is about the subsets of A. So let's look at this set A with 3 numbers, 1, 2, and 3, and the function is defined on A, and the function value gives you a subset of A. Okay, remember the square root B of A means all the subsets of A. So what's the output if you pick up any number A from the set A? It just gives you the set of A and 2. Okay, so So then if you pick up all the elements or numbers in set A, then you're going to get the range of the function, which includes 3 sets. Okay. So if you pick up 1 for A, you get F1. If we pick 2 for A, you get F2. And if we pick 3 for A, you get F3 in the range. So these are in the range. And this is the range of the function. Okay, so this is the definition, remember? So all the function values when you pick the element in the domain. So what is F1? F1 is just the set of 1, 2 by definition. Okay. And what is F of 2? It's just set of 2, 2, but you don't count the repeated numbers, so that's just set of 2. And F of 3 is just a set of 2 numbers, 3 and 2, or 2 and 3. Okay. So the range of the function f is the set of all elements of B that are second coordinates of some element f. But usually that's not a hard thing to figure out. Okay, as we know, if a function is both surjective and then the range is equal to the codomain and vice versa. So this is pretty straightforward. So let's look at a function f from A to B. This theorem says f is surjective if and only if the range is where f is equal to B. So that means you can always find a preimage on the f, right? But that's exactly the definition of a surjective function, isn't it? So the proof only has 1 or 2 sentences. Namely, the function f is surjective if and only if for every element B in the set B, the codomain, is equal to f of A for some A in the domain. That's the definition of a surjective function. And this happens if and only if the set B is equal to the function values, all the function values. When you go through all the elements in the domain, which is exactly the range of the function or the image of the function, isn't it? So that's that. There's not much to say about it. Okay, so then we talk about the inject function, the surject function. Then obviously, if a function is both injective and surjective, we call it bijective function. We already know that, or one-to-one correspondence. And the bijective function is very, very good function because you have one-to-one correspondence and you can define inverse functions and so on. There are a lot of things you can do about it. So, injective functions are called injections and the surjective functions are called surjections. Bijective function is called the bijection. And we have to be careful about the wording here when we say bijective function or bijection. We also say one-to-one correspondence. But that's not the same as one-to-one function. As a one-to-one function means injective, but one-to-one correspondence means bijective. So just be careful when you say this these words. Let's just look at some examples, simple examples. So suppose the set A has three numbers, 1, 2, and 3, and B also has three numbers, 4, 5, and 6. So we got two sets. Then we can define a function f from A to B by those order pairs. Functions are just order pairs, right? And so there are three order pairs: 1, 5, 2 paired with 6, and 3 paired with 4. Okay. So the first coordinate comes from the domain, and the second coordinate, second number in each order pair comes from the codomain. So you can see each element of A occurs exact once as the first coordinate of the order pair. So f is function. So in other words, 1, 2, and 3 all appear exact once. So that makes the f as a function. So we just check that. But at the same time, if you look at the second element of the ordered pairs, each element in the codomain B occurs exactly once as a second coordinate. So first, it appears each number in the set B in the codomain of the codomain appears in all the pairs. So it's onto or surjective, but it appears exactly once. So that makes it one-to-one, right? Different numbers in the domain result in different numbers in the codomain. So that's one-to-one. So it's both one-to-one and onto. So it's bijection or bijective. Okay, the next example, f of x equals 2x plus 1. We have done this example before. And we have shown this function is one-to-one, and later we showed it is also onto. So this function is also a bijection. Actually, if you draw the graph of the function, it's just a straight line with slope 2 and passing through 1 in y-axis. And it passed the horizontal line test, so it's one-to-one, but also for any y value, any real numbers, you can always find a so that's one-to-one. That's onto, but it's also one-to-one because any horizontal line intersects the line exactly once. So it's one-to-one and onto. So it's bijection or bijective. The last example is f of x equal to x minus 1 or x minus 2, and defined on the two sets from R minus set of 2 to the set of R minus the number 1. We discussed this function also before, and we showed that it was injective, and we then showed that it was also surjective. So this function is also in bijective or bijection. And if you draw the graph of the function, you can also easily see that the if you draw the horizontal line, it intersects the curve exactly once whenever the function is defined. Okay, remember the domain and the range. I mean the codomain. So here the codomain is the same as the range. So this is a bijection. Sometimes it might be easy to prove a function is a bijection. Sometimes maybe not so easy. It may not be hard, but it could be tedious, like in this example. But if you draw the graph, then it's much simpler to check the function. If you draw the horizontal line, for all the horizontal lines in the domain, I mean in the range. I'm sorry. It intersects the curve exactly once, right? So so that tells you it is onto and one-to-one. I mean this relation is obviously a function. If you draw the vertical line, it passes the vertical line test. So so there are different ways to show a bijection, but a lot of times it just makes it much easier to draw the graph. So that's the end of this section. Any questions? I guess we just finished this section today, and we're going to do the next section next time, next class. Let's just stop here.